Good afternoon, everyone. Today we're doing a physics experiment with my handy dandy helper.
Hello!
Hi! All right, Sophia, can you take the 4 cups of marshmallows and put them into the microwave?
Without the cup.
Ooh, so she brings up an important point. I took out the microwave rotator and I put a cup over the top. This makes the plate not rotate, so the hot spots are all gonna be really obvious. All right, put it in. Balance it nicely on top of there. And since the plate won't be rotating, the hot spots where the antinodes of the microwaves are going to end up being more obvious, and those will be the spots where the marshmallows melt. All right, let it go for how about a minute and a half.
Unicorn magic.
And what we'll do is we will be waiting to see when the marshmallows start melting. What we don't want to do is put it for a minute and 30 seconds and just wander away. Because if we do that, well, it might explode. You've all seen marshmallows in the microwave get bigger. Fun thing to do around Easter time with the marshmallow puffs or the marshmallow peeps.
Yay!
Yay! So we're keeping a close eye on this. And when we see the melting starting to occur, we're going to pull these guys out.
I smell it.
Right. Oh, I can see some expanding over there on the side. That must be where the antinodes are. Almost time to pull it out. Go.
Look how bubbly they are.
Oh, I see. All right. So with 2 hands, carefully pull it from the microwave. Watch out, there could be some hot spots.
There we go.
Put it on the kitchen counter. Okay. So what I want you to do is, can you find the hot spots in here?
There's probably one right here.
Okay.
Because it was in here. Those probably are. This
Right
one was
here?
already bubbling up.
Oh, that's really warm. Okay, so this is one.
Yep. Ooh, this one's soft and squishy and it's warm.
There's one. Any more in there?
Oh, there's one right here.
There's one right here, okay.
It's pretty much just the 4 corners. There's one right here.
Ooh, this is pretty warm right here.
Yeah, that's
Okay,
like
what
the
I want
middle.
to, oh my gosh, that's so melty. The other marshmallows are getting eaten up by it. All right, what I want you to do is I want you to measure the distance from here to here. The distance between 2 of the hot spots. And can you measure it in the centimeter side, please? Excellent. All right, a little bit over, a little bit over, a little bit over. There, that's the hot spot. How many centimeters is that?
14.
14. Excellent. Now we have enough marshmallows to go make Rice Krispie treats. And then I'll give you the rest of the instructions to find the speed of light in a minute. So what is it we exactly measured? Sophia measured the distance from one hotspot to an adjacent hotspot. Those correspond to the places in the microwave where the food heats up most, but they also correspond to the standing wave's antinodes. So essentially, she measured the distance from one antinode to another. But keep in mind, the distance from one antinode to an adjacent antinode is only half a wavelength. So when she measured a distance of 12 centimeters, that must mean the wavelength of this microwave that's going through our food right here has a wavelength of 24 centimeters. That leaves the only bit of information we need from the back of our microwave. So feel free to do this at home, but because of how microwaves work, I'm going to bet that your frequency is the same as my frequency. In this case, the frequency of our wave is 2,450 megahertz. Before I use this in an equation, I need to remember to convert megahertz to hertz. And why do I think your microwave and my microwave will have the same frequency? Well, that's because both of our microwaves work on the same principle. We're creating standing waves of microwaves in materials. And those are just not any materials. When we put food into the microwave, it always has water in it. And water, represented by this dipole moment molecule over here, vibrates at a specific natural frequency. And since all water is the same across, well, everything we know so far, then that frequency for resonance, for making the standing wave, should always be the same. So then, which equation would we use to find the speed of the microwave? Should we use calculating speed with distance or time? Or wavelength frequency? Pause for a second and see if you pick the same one I do. Got it? I would use the equation on the right. This relates the speed of a wave to its wavelength and frequency. We do have something that is measured as a distance, but it's the distance between two antinodes, or it's actually two complete antinodes. That's not exactly the distance the wave travels, and we have no time information. So let's say we do this problem out. So using the wave equation and substituting in our 24 centimeter wavelength and our 2,450 megahertz frequency, this gives us a speed of 5.88 times 10 to the 8th meters per second. Now, if you're looking at this number and you're like, wow, isn't that a lot bigger than what Ms. Pasega said yesterday? Well, yeah, that's true, but that's because in this experiment, the most common error is not being able to correctly measure the wavelength. I'm guessing in this case, if we couldn't see the exact distance between the two centers of the antinodes of the marshmallows, we might have overestimated our measurement. Now, if you want to try this at home, feel free to try this. You can use marshmallows. You can use Peeps. I've seen it done before with chocolate bars or chocolate chips. The smaller the better, so that you can more accurately measure the wavelength. In this case, they're measuring 7.1 centimeters between the two hotspots, whereas we measured 12, most likely because we didn't measure ours super accurately. I've also seen it done with weird things like cheese or butter spread on toast, or even rolls of sausages and meatballs. In any case, if you want to try this at home, follow the procedure in this video. For today's calculations, we'll be using the speed of light, or rather, all the waves of the electromagnetic spectrum. We'll be using the speed of these electromagnetic waves as 3 times 10 to the 8th meters per second. The goal of your classwork for today, then, is to practice calculating using the new speed of light, as well as being able to distinguish between the 7 different sections of the electromagnetic spectrum. Feel free to use your poster to answer those questions, and feel free to use these 3 equations to answer any of the calculation questions. Okay? Best of luck!